Uh, it is an immense pleasure for me and the Department of Physics to welcome Professor G.P. Dash for this colloquium. Unfortunately, we have to do it today online because of this sudden notification of a closure. So, as a custom, I have to say a few words about today's speaker. Professor G.P. Dash is a very senior and very well known condensed matter physicist. He is also a materials scientist. He is very well known for his enormous contribution in emerging fields of materials, modeling, simulation, and design. A very brief introduction to his career. Uh, okay, if I am allowed to begin from the BSc days, so he got his BSc from St. Xavier's College under Calcutta University at the time, and then did his MSc in Science College under Calcutta University, got his PhD in physics from Bombay University, and did his postdoctoral research in Max Planck Institute in Stuttgart. That is for solid state research. He held several very important positions, say, beginning with the position of scientific officer at BARC Mumbai, and he carried on with that job, I believe, till 2004. And then he was an adjunct professor at IIES Trishipur, distinguished visiting professor at PSG Institute of Advanced Studies Coimbatore, and then he was a senior professor in the Department of Materials Science, IACS Kolkata, for a long period of 12 years, 2006 to 18. And after leaving IACS, he joined IIT Kharagpur as a visiting professor. And apart from this, Professor Das held short-term visiting positions in different places all over the world. For example, in Max Planck Institute for Solid State Research in Stuttgart, Germany, ICTP Trieste, Italy, University of Groningen, Netherlands, Institute of Materials Research, Tohoku University, Japan. Professor Das has a very broad research interest, and when he talked to me over telephone, mentioning several interesting topics for this colloquium, and I actually insisted upon talking about 2D materials. So his research areas are materials simulation and design using first principles DFT, energy materials, hydrogen storage, graphene and related 2D nanostructures, spintronic materials based on dilute magnetics, semiconductor and dilute magnetic oxides, topological materials and quantum structures, cohesive electronic and magnetic properties of ordered and disordered quantum systems, and several other very, very um, intriguing, interesting, and sparkling fields actually. And it's definitely Professor Das received many awards and recognitions. Just I can mention a few. He won the ACC MS International Award by the Asian Consortium on Computational Material Science in recognition of high-level research work on computer-aided design of materials. He held the chair of PSIK 2020 Theme Symposium in Lausanne, Switzerland. He was a distinguished speaker, Wright-Patterson Air Force Base, Ohio. He is guest editor and editor of many journals. He is associated with several frontline journals in physics as expected. He guided several PhD students, and he has a publication, I believe, over 150, and with age index 28 as far as I know right now. And so uh, we have a very distinguished speaker with us today. And Professor Das also served in different national and international committees, and I have a pretty long list before me. And I don't think I will be reading them out because that will exhaust his time of talk. So we are very honored, Professor Das Gouda, for me to have you with us, speaking to us, to our students. And now I invite you to deliver your talk. The screen is all yours now, and the audience as well. Gouda, please.
Thank you. Thank you very much, Urunavu, for your very kind and elaborate introduction. Well, I do not know to what extent I deserve it, well, I mean, Presidency College and now University is really very close to my heart. I wished that I will go and visit the same Baker's Lab corridor, because it is so nostalgic. This is the place where I had attended the courses by Professor Shyamol Sengupta and Professor Amol Roy Chaudhuri. Some of the things which I will never ever be able to forget in my entire life. And in fact, those were the formative period that I had spent in Presidency College at that time, and the year was 1974, 1974-75. That was the year when we used to attend those classes. So it's really very nostalgic. Okay, so as Arunabha pointed out that, he was asking me as to which topic I'm going to talk on. So I gave him several options. Then he suggested me 2D materials. And so this is the title, 2D materials renaissance. So I'll keep in mind that the audience is mostly consisting of physics students, postdocs, and that is the level at which I have kept it. But if there are some, experts in the audience, I think I will be excused for the simplicity of the level at which I'll deliver the talk. Okay, so let me start. Here it is. Can you see the full screen now? Yes?
Yes, go, we can see it. Yeah.
Thank you. Thank you. Okay, so, when we start our career, we are told by our parents and our teachers that we will do either physics or chemistry or biology. Now, in my own perspective, physics is intimately linked to originality, chemistry is linked to diversity, and biology is linked to complexity. And all the three together, they constitute what we call reality, and that is life and nature. And it is really intriguing that this particular element in the periodic table, carbon, is something which plays an important role in all these three branches, whether it is physics or chemistry or biology. I think this is probably the unique element, apart from hydrogen, of course, which is truly ubiquitous. Okay, and as I proceed, you will realize that. Now, again, starting from a very simple college level or even school level physics, let me start with the carbon, the two allotropes which every student knows. Namely, it has got graphite and diamond. Now, graphite is sp2 bonded, and it is, obviously, covalently bonded planes held together by a weak interplanar van der Waals bonding between the planes. Okay, and this can be easily broken. This van der Waals bonding between the plane can easily be broken, and so there is no dangling bond on in that particular plane. Whereas, in contrast, diamond, which is sp3 bonded, all of you know, it is covalently bonded in 3D. And when it is cut along any direction, it will leave dangling bonds that are chemically and energetically unstable. If you try to cut a diamond from in any plane, there will be dangling bonds that are chemically as well as energetically unstable, and they can force the material to rearrange its structure to lower its surface energy. This is something which is absolutely rudimentary level physics and chemistry of carbon allotropes. Now, somehow or the other, if you can manage to remove this weak link between the two planes in a graphite, okay, it can be made much stronger, much stronger. Such a single layer of carbon is called graphene and has a tensile strength which is 1,000 times greater than graphite. So, in graphite, the commonest example is, of course, a pencil, which we use for writing, and a pencil breaks easily, but that breaking is in this weak link that is between the planes. That's very weak when a van der Waals bonding. However, if we can somehow manage to remove that weak link and retain only the single layer, then it becomes 100 times stronger than steel. This is an unimaginable number. Okay, and look at the other superlatives here. It is not only the strongest material, the single layer of carbon. It is not only the strongest material with a Young's modulus 1 TPa, terapascal, huge. It is the best thermal conductor, which is much more than that of copper. It's about 5,000 watt per millikelvin. Then meter Kelvin. Best electrical conductor at room temperature, which is the J, the current density is 10 to the power 6 milliampere per micron, and it is optically transparent. Only 2.3% of the of the electromagnetic radiation passes through that. So there are many others which we will come. So this is very intriguing that such a simple honeycomb kind of a lattice, if we can manage to produce, it will have such exceptionally high list of superlatives. Now, there is another thing which is intriguing in carbon, namely, there are various nano allotropes of carbon which we all are aware of by reducing the dimensionality from 3D to 2D to 1D to 0D. Okay, and what happens is that when you reduce the dimensionality, it reveals all kinds of bonding. We can call it SPX. It is not only sp2 or sp3, but it can be spx, where x can vary anywhere between 1 and 3. And these varieties of allotropic structures are known to us now very much, namely fullerenes, which is like a football, as you know, and nanotubes. And of course, graphite is already there. And it is the graphene which can be considered to be the mother of all. Because if you roll a graphene sheet, you get a nanotube. If you wrap a graphene sheet, you get a fullerene. If you stack a graphene sheets, you can get graphite, and so on and so forth. So graphene can really be conjectured as the mother of all. Now, the manifestation of the unique properties of graphene comes because of some reasons which we have read in our early college days. For example, electronic properties are different because of the fact that here we have got electrons confined within a plane, confinement of electrons. The optical properties change because of the reduced dielectric screening. The mechanical properties are different because of the flexible elastic behavior. If you try to find out the elastic coefficients, you will easily discover why the mechanical properties of graphene is so much different from others. Chemical reactivity is very, very different because it is more surface to volume ratio. The surface to volume ratio, if it increases, obviously it is exposed to the atmosphere, and there will be more and more chemical reactivity. Similarly, electrical conductivity and many other properties, are unique properties, are getting manifested in carbon. So today I decided to give the talk in the following flow. First, that I mentioned about carbon, which is a unique element in the periodic table that I already told you. And now I will come to the first real 2D material in nature, which is called graphene, and what is its basic physics. After that, I will tell you about the graphene-inspired other 2D materials that have been discovered experimentally, and also there is a lot of computer simulation work which has gone by, and indeed it is an area which is by no means saturated today. It is continuously getting more and more expanded. So I will touch upon the various 2D materials diaspora. It is too big, but I will try to give you a kind of a flavor. Then I will mention about the density functional theory, which Professor Arunav Chakraborty mentioned in the beginning. So density functional theory is an indispensable tool for understanding the microscopic properties of these 2D materials. both pure as well as functionalized variants. And I will mention some of the examples that we have ourselves done in our group. Then the functionalization of graphene leads to different kinds of applications, and these novel applications also, at least a few, because there are so many applications, it is impossible for me to tell about all these things in one lecture, but at least a few of the applications I'll mention before I conclude. So how was graphene discovered? These two gentlemen, Andrei Geim and Konstantin Novoselov, wrote a paper in Science in 2004, where they succeeded in producing, isolating, identifying, and characterizing a single atomic layer of carbon. And it is truly interesting how such a simple kind of a result leads to a Nobel Prize, but there is a very, very legitimate reason, which you will realize as I proceed. And 2004 paper led to a Nobel Prize in 2010, which is only 6 years. This is one of the fastest. There are, of course, other examples, like, for example, GMR, which was giant magnetoresistance, which was discovered in 1988 by Albert Fert and Peter Grünberg, one in France and other in Germany. Within 6 to 7 years, they got Nobel Prize. So there are a few other examples, but also there are examples like Van Vleck, who had to wait for, or our own Chandrasekhar, who had to wait for more than half a century to get a Nobel Prize. But anyway, that's besides the point. Now, depending on whether it is a pristine graphene or it is a doped graphene, there are some variations which I will discuss as I proceed. But how did this Andrei Geim and Novoselov got the graphene sheet? That is something which is unimaginably simple. What they did is that what is called the exfoliation technique. This is a top-down approach. What they did is that they took some kind of a scotch tape procedure. So there is a substrate which of course has got carbon, and they took a scotch tape and just quickly take out the scotch tape. You can do it even in your house, okay? And you will find that essentially 1 or 2 or 3 or 4 layers of carbon just get pasted onto that particular sheet. And nobody before Geim and Novoselov could imagine that it is possible to synthesize a atomically thin layer in such a mundane approach. So this gave rise to a real revelation to many, okay? And later on, people tried to exfoliate not mechanically, but also chemically. Chemical exfoliation is something which is very, very common. But then as we proceeded in the first century, in the first decade of this century, there were many groups who tried, apart from this, the exfoliation technique, they tried, for example, the CVD, the chemical vapor deposition, which of course is a bottom-up approach to produce better quality graphene sheet, which is highly scalable. So it is possible to get a single layer graphene, bi-layer graphene, tri-layer graphene, and so on. And you can truly identify using a simple, optical microscope, whether it is a single layer or bi-layer or tri-layer or something like that. Okay, and this is the kind of optical microscope picture where you can see the different colors, and the different colors actually correspond to different thicknesses of the graphene sheet that come out in this scotch tape approach. And if you do a more sophisticated STM, that is called scanning tunneling microscopy, Binig and Rohrer in the German-speaking part of Switzerland came up with this amazing discovery in the mid-1980s, which is called scanning tunneling microscopy, which I will say that is the absolutely the essential experimental tool for probing any kind of nanomaterials or nanostructures. And look here, a graphene sheet, you can actually see the hexagons, and here I have just superimposed on that these hexagons of carbon on these I mean the blackish blocks. You can see that. So this is something which you can actually see in a scanning tunneling microscope. If you want to know more about these different synthetic methods, I think you can have a look at one of the very early review articles by Andre Geim and collaborators, which is called, the review is entitled Graphene, the Status and Prospects, which appeared in Science in 2009. Very nicely written review article. Okay, so these are some of the other pictures which I will just skip. Okay, of these are all graphene specs of different thicknesses, and the pictures that you are observing are all actually ordinary optical microscope which you use in a standard laboratory in a college. Okay, and look at this I forgot to tell. So this size of this, I mean, in the lateral dimension is of the order of 100 nanometer to a micron. This length is of the order of while thickness is of the order of a nanometer, the lateral dimension is of the order of 100 nanometers to even a micron. Okay, that is the interesting stuff. Well, but is it that the graphene was not known to people before 2004? That is not correct. Actually, there were many people starting from 1859, okay, when Benjamin Brodie discovered what is called graphone. He called it graphone. And then in 1947, Wallace predicted the graphene band structure, which I will show after some time. Okay, and this paper is really interesting. I mean, he came up with the essential band structure of graphene with a Dirac cone, which I will discuss way back in 1947. But his intention was definitely different. He did not know anything like the fact that this miracle material graphene exists. No, he wanted to find out the electronic structure of graphite. Graphite is a very well-known thing, and Wallace wanted to understand the electronic structure of graphite. But you will see very soon, I will show you how Wallace was almost as close to what we are getting today using density functional theory, which I will show. So then after that, in 1948, 62, 87, okay, and even in 1990, there were attempts for finding out the synthesizing monolayers of graphite. But it was only Geim and Novoselov in 2004 that they succeeded in exfoliating the monolayer graphene, and not only succeeded in exfoliating, but also trying to find out its characterizing it and trying to find out its properties, some of which I will tell you very soon. And then, as all of us know, in 2010 they got the Nobel Prize, and so on. So and after that, the number of papers that started coming in the field of graphene is really increasing exponentially. Okay, and also the applications, which you don't have to bother now here, because I will discuss some of the applications in sensors, in transistors, in biology, and even in medicines. I will discuss a few of them. Even in DNA sequencing, today graphene is used. Now, the graphene applications is so wide, starting from the composites and coatings, okay, to membranes, okay, for drinking water. Okay, you know that RO drinking water, which we all use in our house. Okay, so can we use graphene as a membrane for the drinking water? Okay, or for purifying water. Okay, then energy materials. Okay, so how it is possible for us to get some kind of a battery in a very, very small dimension, which can be used in smartphone. Biomedical applications, I will discuss a little bit. Sensor applications, electronics, of course, transistors. So graphene has the potential to radically change our world from industry to medicine to electronics. There is virtually no aspect of modern civilization that graphene won't transform. That is the kind of a disruptive, discovery. It is truly disruptive discovery that was made by Andrei Geim and Konstantin Novoselov. And that is why there are some people who are of the opinion that if you combine all graphene's amazing property, it could create an impact of the scale that was last seen with the Industrial Revolution. This is not a overstatement. This is really a truth, as you will see as I proceed. Now, it is nearly 20 years. 2004, it was discovered, and it's nearly 20 years today, 2023. And graphene, as well as graphene-inspired 2D materials, they continue to throw surprises even today. Okay. For example, there is a superconductivity that has been discovered recently in bilayer graphene, which I will touch upon towards the end of my talk. So it is not only the application potential, but also in terms of the basic physics. Okay, interesting. Now, let me just tell you a little bit about the physics of graphene. Now, the common sense tells us that all natural materials are 3D. When you look around you, okay, there are a large number of things which are either metallic or semiconducting or insulating. Yeah, but whatever it is, these are all 3D materials, which has got a length, a breadth, and a height. Okay. Now, does a pure 2D material exist in nature? This is a very fundamental question that was asked way back in the middle of the last century, slightly after that, by two guys. One was by Marmin Wagner in 1966. They came up with a paper in Physical Review Letter. And the other one was by Pierre Hohenberg, whose paper came in 1967. And so this is called Marmin Wagner Hohenberg MWH theorem. What does the theorem state? Marmin Wagner stated that infinite ideal 2D crystal are not stable. They gave an example through magnetism, but they showed, they rigorously proved in this paper in PRL 1966 that infinite ideal 2D crystals are not stable. Pierre Hohenberg, who was not aware of Marmin Wagner's work, he independently proved in 1967 in Physical Review paper that the impossibility of long-range order in a superfluid or superconductor at non-zero temperature in either 1D or 2D. Now, these two papers are very interesting in their own right. I unfortunately do not have time to, to discuss it in details. But, Bat Halperin, who is a very celebrated theorist, wrote a paper as recently as in 2019 in Journal of Statistical Physics. I will tell those of you who are interested, please see this paper of Bat Halperin, okay, who actually said that it was Hohenberg who came up with this paper first, before Marmin Wagner, but because PRL publishes it fast, so this PRL paper appeared before, a few weeks before the Physical Review paper of Hohenberg. But it was Hohenberg's work which came before Marmin Wagner's. But anyway, that's beside the point, since these two are. But interestingly, this even much earlier in 1935 and 1937, these Peierls and Landau, in fact, they were people of different grades altogether. So they actually proved or not proved, but they actually suggested that long wavelength phonons break the translational symmetry. So the MWH theorem, the Marmin-Wagner-Hohenberg, states that 2D systems with a continuous symmetry cannot be ordered. That is, cannot spontaneously break that symmetry. It illustrates the fact that as we go to lower dimensionality, fluctuations become more important. And for d less than equal to 2, they destroy any potential ordering. Well, what does that mean? Does that mean, well, I'll skip the Coleman's field theoretical treatment, but forget about the top part, go to the bottom part of this. So prior to the discovery of graphene, the HMT theorem was used to argue that purely 2D materials would not be stable. But yet graphene exists, very much exists, and has very good mechanical property. It's a pure 2D. So are the predictions of HMW, that is Weinberg Marmin Wagner theorem, inapplicable in this case, or are they still observable? Are there still observable effects of the theorem at large scale? Now, this is something which is a very interesting question posed to theorists. Okay, and here I would just like to touch upon something which is called flexural mode of phonons. Now, those of you who are aware of the flexural mode of phonon, it will be nothing new. But those of you who do not know, let me tell you some textbook stuff about phonons. Now, you know, what are phonons? Phonons are nothing but lattice vibration. Now, what kind of lattice vibration are they? I mean, this is where, you know, I miss the class. You know, if I would have been in the class, I would have explained to you how the acoustic phonon versus optical phonon, which is acoustic phonons which are called LATA and ZA, optical phonon LOTO and ZO. What is the difference? Okay, it is nothing but the different modes. Okay, either it is a kind of a mode along the plane, okay, or it is a mode which is called breathing mode or perpendicular to the plane. So depending on that, it is either an acoustic branch. Okay, these are the branches of phonons, or it is an optical branch. But there is something called flexural mode. Flexural mode is something which is perpendicular to the plane of the graphene in the case of graphene. Okay, and if you look at the the phonon density of state, the phonon dispersion, you see the ones which are starting from zero, these are called acoustic mode, yes, and the ones which are here, these are called optical modes. See, there are three, okay, modes here. One is LA, another is TA, and the one which is parabolic here. See, LA and TA are linear at zero, but this is parabolic. So this is what is known as the flexural mode. And here is a in the inset I have shown the flexural mode. Look at the flexural mode which cuts at the M point, okay, and this is the kind of a dispersion which is there for the flexural mode. And this flexural mode is something which in case of graphene is responsible for its stability. I will and in fact that is one of the reasons why we have done the detailed calculations for the phonon modes, not only in graphene but also in the other analogues of graphene like silicene or germanium or stannine or phosphorine and things like that, which I will come as I proceed. Okay, so where do we stand? So we are now convinced that graphene is the first real 2D material with a unique linear band dispersion or a Dirac cone. And this is the kind of a Dirac cone. And the dispersion is truly linear, completely linear dispersion. Okay. So how is the lattice looking like? Cannot be anything simpler than this. It is a just ordinary pattern of hexagon. And there are two kinds of atoms. It's called A and B type of atom, the red and the blue. And this is why it is called a 2D bipartite lattice that shows a semi-metallic behavior. I'm sure you know what is a semi-metallic behavior, where the density of state at Fermi level is zero. Okay, if there is a gap, it becomes a semiconductor. And if it is metallic, then it is overlapping. But if it is semi-metallic, then it is neither metallic nor in semiconducting, but it is just touching at the Fermi level. So it has the graphene has got a strong in plane and a much weaker interplane bonding. And the thing which I will impress upon you is that it's a massless Dirac fermion, where you in place of the velocity of light c, we replace it by what is known as the group velocity of the electron, which is VF, the Fermi velocity. Okay, and we replace the spins by pseudo spins. Now, in order to solve the electronic structure of graphene with almost massless nature of the fermions, we solve the instead of non-relativistic Schrodinger equation, we solve the relativistic Dirac equation, which, as you know, is first order in time. I do not want to go to the classroom, lectures which you have all attended as to why we go from Schrodinger picture to the Klein-Gordon picture to the Dirac picture. Okay, but anyway, just for the sake of completion, I have put this particular slide, namely, as you all know, that in Schrodinger equation, it is second order in x and is the first order in time. But then when we go to Klein-Gordon, it becomes something which is second order in time. But unfortunately, here the particles conservation is facing a huge problem, and that is where Dirac came for the rescue to suggest something which is first order in time. And there is an interesting history of science where Niels Bohr once was asking, what are you working on, Mr. Dirac? And Paul Dirac answered that I'm trying to take the square root of something. And that is where the brilliance of Dirac came. Dirac found out the square root of the momentum operator without finding out the square root. This is something which only Dirac can think of. He could, any standard textbook of quantum mechanics will give you the proof where the square root of the momentum p square operator is something which is written as px sigma x plus py sigma y plus m sigma z. This is a linear combination of the so-called Pauli spin matrices. Okay, and the Dirac matrices, and here the square root is obtained by a linear combination, and that is what was the Dirac's solution in 1928. So in case of graphene, what was found is the following, that in a massive particle, electron is considered as a particle with mass, so I call it massive particle. This word massive, don't take it figuratively. Massive means something which has got a mass. Okay, and E square equal to P square C square plus M square C to the power 4, which you have read in your quantum mechanics. So E equal to square root. Now, if you expand it, then you will see that this is something which looks like a parabolic dispersion. Whereas if you put the mass equal to 0, okay, for example, a photon, then E becomes equal to what? Forget about this first term, then equal to E becomes equal to plus minus PC, C times P. So the E versus P is becoming now a straight line, not a parabola. It is not P square, but it is P. So it's a straight line. So this is something which in electrodynamics we have read. Okay, but in any standard textbook of electronics, we are used to saying, okay, conduction band and valence band, they look like this. This is parabolic. Okay, gallium arsenide, for example, you will draw the conduction band like this and the valence band like this, and then go ahead and solve the Richardson-Dushman and all other equations which you have done in your electronics. Okay. Now, in case of graphene, the scenario is different. Look at the band structure. Okay, the pi band and the sigma band. The sigma band is the one which is in the plane of the graphene, and the pi band is perpendicular to the plane of the graphene. Well, this is not a band, this is a bond. So the bond is connected to the band. Okay, this is the pi bond, this is the sigma bond, this is the pi band, this is the sigma band. And look, the pi band is crossing at the so-called Fermi level or chemical potential. And how is it crossing? It is linear in its dispersion. Okay, that is where the difference lies between a semiconductor and a graphene. Instead of parabolic relationship, we have got linear dispersion. Okay, so one can understand the electronic structure of graphene based on a simple, very simple tight binding model, which was done as I mentioned in the beginning of my lecture today, the tight binding model by Waals in 1947. Look at this. This particular, this entire thing has been just copied from that 1947 physical review paper of P.R. Waals. So what they did is that with the back of the envelope calculation, there was no computer in those days, by the way. He did not use computer, at least. So he took a pen and pencil and came up with the relationship between energy and K. So E-K relationship, E as a function of K was given like this. Now plot it. If you plot it, then you will find this kind of a E versus K relationship as you go along the high symmetry directions. Okay? And interestingly, that at K point, this K point is a high symmetry point. Okay? So gamma MK, that is a high symmetry direction. At K point, the dispersion of the bands is linear. If you expand it, it will become directly a straight line. And that is what was first found out by Waals in 1947. Remember that. Now, there is a quasi-particle zoo in condensed matter physics, which, because of the lack of time, I cannot go into. But as you know, that there are Schrödinger fermions and Dirac fermions. And in case of Schrödinger, it is H is p square by 2m. In case of Dirac, the ultra-relativistic particle, it is H is given as C times sigma dot p. Now, in case of graphene, it is exactly something which is mimicking this ultra-relativistic Dirac equation. It only difference is that instead of C, that is the velocity of light, you have got Vf, which is the Fermi velocity. And what is the value of the Fermi velocity? In case of graphene, it is typically 100th or 1/300th of the velocity of light. It is about 10 to the power 6 meters per second. Okay, whereas light is 3 to 10 to the power 8. So 2 orders of magnitude lower. So the value of Vf, but still it is pretty high. So that means the electrons are really flowing in graphene unhindered. Now, whether this is a boon or a bane, you will have to decide, because remember that for transistor making, you cannot afford to have electrons flowing so fast. You have to have a semiconducting behavior in order to ensure that a material can be used as a semiconductor. So, can graphene not be used for a semiconductor? That's the $1 million question, and we will answer that very soon. Okay, so to wind up this part of the Dirac material, let me just tell you the last point, that the most celebrated Dirac material is graphene. It's a two-dimensional monolayer of carbon where the massless while points are nothing but the Dirac point, separated out into 4x4 matrices, separated out into 2x2 matrices. That's called the Weil excitation or Weil fermions. Okay, and so in case of graphene, you get this. Here it is. The electronic band structure at K point. Look, it is a straight line, absolute straight line, right at this point, and that is what is giving rise to the Fermi surface, which is the shark tooth, the 6-point shark tooth pattern. There are 6 points, 1, 2, 3, 4, 5, 6. You see, there are 6 points, and it's exactly like a shark tooth. And the electronic density of state looks like this. Okay, and look, it is semi-metallic. It is 0 at the Fermi level. And the phonon dispersion I already showed you as to what is the LA and the TA and the flexural mode ZA. And it is the flexural mode that is something which is crossing at the K point. Look at that. So the flexural mode is very important. And this flexural mode is something which gives rise to the deviation from the pure 2D-ness of the graphene, which is the undulations of the graphene, which I will touch upon after some time. But look at the experiment. This is the angle dissolved photoemission spectrum of graphene, a pure graphene sheet. Okay, and look, this is the Fermi level, and this is the angle dissolved photoemission. E versus K, as you know, can be obtained. And here, look, it is exactly like a V-shaped curve. And this V-shaped curve is nothing but this V-shaped. Look at this V-shaped. This V-shaped and this V-shaped are same. Now you can ask the question, what about the above the Fermi level? above the Fermi level is also a V-shaped, but that we cannot determine experimentally in a um, angle dissolved photoemission. You have to do what is known as the inverse photoemission. If you do that, then you can also get this part of the cone, the upper part of the cone. But here you can see the lower part of the cone experimentally. So this is not utopia. This is a fact. Okay. Then there is something called pseudospin. Because of the lack of time, I can see in my watch that my time is running out. So the pseudospin is something which is just line joining the two in equivalent points, the red and the blue I showed you, and how the precision of this line, which exactly something mimics that of ordinary spin, it is called pseudospin. Okay, now whatever there's a time left for me, I will tell you about the other 2D materials which are inspired by graphene. So, motivated by the successful discovery and application of graphene, scientists tried hard to see what are the other 2D materials. And this is where they found out a whole lot of other family members of 2D materials that can be created using a graphene analogy. Namely, there's a strong in-plane covalent bond plus a weak van der Waals coupling between the layers. And what they did is that they, this is an example which I have given. For example, take hexagonal boron nitride. As you know, boron is just one below carbon and nitrogen is just one above carbon. So hexagonal boron nitride is isostructural with graphene, and also it is isoelectronic. Now, these boron nitride nanoribbons have been deposited on a zinc sulfide template. Because of the lattice matching, it grows very nicely. And then what they do is that they heat it, and at 1100 degrees centigrade, the zinc sulfide vaporizes, because zinc sulfide cannot withstand beyond 1100. But you know what is the melting temperature of boron nitride? It is 3000 degrees centigrade. So if you deposit boron nitride on zinc sulfide, and then after it is deposited, you just heat the whole damn thing, and above 1100 degrees centigrade, the zinc sulfide just goes off, and what remains is only the hexagonal boron nitride. So this way, people started cheating nature. So now there is a whole lot of the 2D materials diaspora. Okay, this will take me a long time, so I have written a smaller version here. This smaller version is same as this. So look at this. We have got graphene family, we have got hexagonal boron nitride, we have got transition metal dichalcogenides, MX2 kind of a family. This is this, yeah. You see, TMDCs are called transition metal dichalcogenides. Okay. So these are MX2, where M is a transition metal and X is either a sulfur or a selenium or a tellurium. So this is one of the most interesting 2D or quasi 2D materials family other than graphene. Of course, in the graphene family itself, it has got its own cousins like silicene or germanium or stannine. But unfortunately, none of these can be synthesized as a freestanding form like what I told you earlier. Namely, the graphene can be obtained as a freestanding monolayer thick material, okay, from exfoliation. That cannot be done in case of silicene or germanium or stannine. There is a lot of work. We have also done some work on silicene, but I will not discuss those things here. So there are also other very interesting families like phosphorine or black phosphorus, which has come. And more recently, there are topological insulators and oxides. I mean, this is unbelievable. TiO2, which is all along we used to know that titanium dioxide is something which is 3D. Okay, there are 3D variants of titanium dioxide which is produced in tons. But today it is possible to synthesize TiO2 as a 2D material. Similarly, chromium trioxide, CRI3, this is used as a 2D magnet two-dimensional magnet. It is like there are easily a huge number of materials in this 2D materials diaspora. So electronically speaking, whether it is graphene or HBN or TMDC, it can be either a conductor or an insulator or a semiconductor. So you can make your own kind of a heterojunctions by putting one layer on the top of the other. And remember that for these heterojunctions, you need not worry about the lattice matching or the kind of bonding like in gallium arsenide, gallium aluminum arsenide so much, because here the in between the plane bonding is very weak van der Waals bonding, and that is something which is giving you a different kind of a spanner for finding out an emerging array of heterostructures, which are called van der Waals heterostructures, and a lot of activities are going on this in the recent past all over the world. These are the different materials having different band gaps. You see the band gaps have been shown. Graphene is of course a semi-metal. It is 0 here, but there are others. Look, this is the band gap. Very small, increasing, and finally look, HBN has got a band gap which is as high as that of diamond. It's a very huge band gap, okay? About 5 electrons. Graphene, MOS2, HBN, and so on and so forth. Okay. One thing I must point out, that is the Raman scattering is something which is absolutely an essential tool in order to characterize the 2D material. The so-called D and the G peaks of the Raman band is absolutely indispensable if you want to really characterize any 2D material. So Raman scattering, we can proudly say, is probably the most indispensable tool for studying the 2D materials. Okay. So I must touch upon the density functional theory, even though this is not a DFT lecture. Maybe Orunabho can arrange another talk where I can discuss about the density functional theory.
Yes, surely.
Probably. Yeah. So here I will skip this, even though this is very close to my heart. How the many-body problem can be reduced by a variational method to a self-consistent one-electron problem via what is known as the Kohn-Sham equation. I unfortunately do not have time to go into it here, but take it from me, those of you who do not know DFT, take it from me that this density functional theory by Hohenberg Kohn-Sham in 1964-65 is probably the workhorse for studying any of these energy materials or 2D materials that we are talking about. And of course, as you know, the Walter Kohn got the Nobel Prize in 1998 for these two papers, the inhomogeneous electron gas in 1964 by Hohenberg and Kohn. It is the same Hohenberg whose name I mentioned some time back, and the second paper in 1965 by Kohn and Sham, and both these papers have the citation which is unbelievable. These are the top 20 highest citation classic papers in APS journals. That are 18 of them are on DFT. Somebody has counted. Nicola Marzari, I met him in Lausanne in Switzerland last August, and he mentioned this. He found out that the 20 highest cited papers, out of which all the ones which are in red, they are all related to DFT. Okay, it's unbelievable, absolutely. And Orunabho knows that on 9th March 2023, which was the centenary of Walter Kohn's birthday, who was born on 9th March 1923, we organized a Walter Kohn centenary celebration on the life, science, and legacy of Walter Kohn. He's a fascinating person. So another time we will discuss about that. But anyway, so let me just end up in the last 10. Do I have 10 minutes, Orunabho?
Yes.
We have 10 minutes,
sure.
right? Okay.
Yeah.
Okay, fine. So I think I should be able to wind up in 10 minutes. So now let us see, let us come to the application, because you might think, okay, we have discussed the physics and this, that, but for what? Why are we studying? Why are we interested in this material? So there are different routes that have been adopted for functionalizing the 2D materials. As I told you some time back that unfortunately the graphene has got a zero band gap, and the electrons are flowing with a reckless speed, 1/100th of that of the velocity of light. Unbelievable. So can it be used as a transistor? No. I mean, for pure graphene, no. So something has to be done, and that's something you can call functionalization. Okay. So people have tried to functionalize graphene and all other 2D materials by doing different kinds of games. One is tweaking the buckling parameter, by doing band gap engineering via chemical functionalization, by introducing vacancies, dopants, periodic tables, periodic holes, which are called via what is known as the ion beam lithography. I'll give you one example on this. Okay, graphene nanoribbons via the zigzag and the armchair edges. By taking a scissor, you can cut graphene into nanoribbons. Use suitable substrates and utilize the screening effect due to the appearance of the substrate. Produce vertical and lateral heterojunctions like what I showed you just in the last slide. Bilayer and twisted bilayer graphenes, which has become a recent craze for people who tried to see superconductivity in it. Then there are pentagraphenes and application of in-plane stress to break the hexagonal symmetry. We have done some work on molybdenum disulfide for thermoelectric behavior, and the paper came out just last week on this. And there are many other ways, but the one or two of these I will mention. Look, for example, take a sheet of graphene. Here is a graphene sheet on the left hand side, and just flash hydrogen on it. Nothing. Just take the graphene single sheet and flash hydrogen. The red ones are hydrogen. If you flash hydrogen, without going into the details, I can only tell you that hydrogen will go and cap the dangling bonds, and it will immediately open up a gap. Look at the gap. The huge gap gets opened up, about 5 electron volt. What do you have to do? Just flash hydrogen on the top of it. You can also flash fluorine or chlorine or iodine. But anyway, doesn't matter. And this is something which SOFO had shown, and we have done some work. My student in ISCS, they did some work on the conformers of graphene and so on and so forth. But anyway, that's a matter of details. All that I wanted to tell you is that the functionalization of graphene, one example I have given. Another example, take a scissor and cut the graphene either along the so-called armchair direction or along the zigzag direction. Look, this is called zigzag, and this is called armchair. Look, this is looking like an armchair. So depends on how you will put your scissor. Will you put the scissor along this or along this? Okay, depending on that, which it is called ZGNR or zigzag graphene nanoribbon, or AGNR, that is, armchair graphene nanoribbons. And the band gap opens up. Look, I mean, depending on the thickness of that. So this is the armchair, this is the zigzag. Now, electronically, because of the edge effects, they are different. See, in one case, there is a gap which is opening up at K point. Okay, whereas in the other case, at the two K and K prime points, it is staying put. Nothing happens. Only the dispersion changes. So there is no gap at K and K prime point in case of a zigzag. But in case of an armchair, there is a gap which is opening. Now look, depending on what is the thickness. And this is something which can be actually seen in experiment. Okay, how to open up the band gap by just tailoring the graphene. This is something which one of my students did. That is, okay, now can we sort of use the defected graphene sheet for the purpose of making some device, some electronic device? The answer is yes. Those of you who have got the electronics background, there is something called rectification. What is the rectification? Rectification means I versus V. Okay, this is I, this is positive V, this is negative V. Look, when you go to positive V, the I versus positive V, the way it is behaving, I versus negative V, it is not behaving like that. This is called rectification. a standard electronic book tells you. It shows rectification. But something more, it is called negative differential resistance. What is that? If our Ohm's law tells us that as you increase the voltage, the current is proportional. That means voltage you increase, I also increases. But look here, the I decreases. As voltage increases, I decreases. This is called negative differential resistance. Now, both the rectification behavior as well as the negative differential resistance behavior is highly desirable for somebody who is a device physicist. More details I cannot tell you, but those who are interested, this paper came out, in the last decade. Okay, the first principles design of how the rectification and negative differential resistance. Okay, so application list, it's a plethora. Transistors, field effect transistors, energy harvesting, flexible and biosensors. Look at this. This is the way. I mean, people are trying to find out the flexible transistors. Look at how the transistors look like. I have actually seen this in when I was in Seoul in South Korea. They have actually this company. What is that? Samsung. Samsung has actually come up with this kind of flexible transistor. See, this is hold in hand. So this is possible using graphene. Okay. Achha. Then gate dielectric, multiferroic devices, photodetectors, battery electrode, optoelectronics, topological insulators, twistronics, valitronics, wearable fabrics. Wearable fabrics. This is a big industry now. People are now, if you go to say Gour market, maybe after some time you will find a kind of a jacket which is made of graphene. And yeah, indeed, the flexible thing, the t-shirt, the shoes. I mean, this is unbelievable. I mean, where it is going. Okay, and remember, this is not just like ordinary one, because there are ways in which the shoes can be used with pores that will prevent you from any kind of a sweating and this that. All kinds of additional features have been then you can have the watches which can be integrated to your wristband and so on. Then there are 2D magnets and there are DNA sequencing. Since the time is not there, let me just tell you. Okay, this is something which I cannot help mentioning. Something which is relatively more recent, twistronics. So take two graphene sheets, just like two graph papers. If you take transparent, put one on the top of the other, and just rotate one with respect to the other by some small degree, 1 or 2 or 3 or 4 degree, and you will see a very, very nice pattern developing. This experiment you can do at home. Take two graph papers which are transparent and put exactly one on the top of the other so that you do not know whether it is 1 or 2. But now, just with respect to one, you just rotate the other one by something like 1 or 2 degree, and you will see this pattern. It's called Moire pattern. And lo and behold, that for graphene with a angle which is 1 point something degree, they found some superconductivity, and this is opening up a new field which is called twistronics. This is unbelievable, absolutely, how it is possible for us to imagine a superconducting behavior in a twisted bilayer graphene. And now there is a lot of experimental and theoretical work which has gone in this field. This is the last one which probably I will mention, and that is how it is used for DNA sequencing. Now look, this is a graphene sheet, and by you can make a hole in this very nicely. You can make a hole and pull a DNA helix through this. And as you know that there are ATGC. Okay, now when it is crossing, when you are pulling it, when it is facing A, then whatever be the current which is flowing in the orthogonal direction is something. When instead of A it is T, it is something else. When it is G, it is something else. So when billions of ATGC are going, you can actually do the DNA sequencing all in a computer. by just using a graphene sheet and pulling the DNA. Unbelievable, I think. And before the graphene, it was done by biologists, but not with this kind of precision, because the biologists could not imagine something which is just a one atomic thick, sheet. Okay, that was impossible for them to conjecture, but today it is possible. This is a work which we did some time back. That is, if you take hexagonal boron nitride, which exactly looks like graphene, and put it on nickel 111, then it shows a very interesting oxidative behavior. See, this is the molecular dynamics which we have done. So O2, this is a O2 oxygen, which we have tried to bring on the top of a hexagonal boron nitride sheet. But by doing a first principles molecular dynamics, we found that the O2 does not stay here. So it does not, the hexagonal boron nitride sheet does not like the O2, so the O2 is going away. Okay, it is repelled. But you put the same hexagonal boron nitride on a nickel 111 substrate, and for your information, hexagonal boron nitride has got a lattice matching with nickel 111. So you put this hexagonal boron nitride on nickel 111, and you will see that the oxygen stays, and the oxygen stays on this hexagonal boron nitride when it is put as an overlayer on nickel 111. Question is why? And something more interesting, not only that the oxygen stays, but the OO distance gets a little bit expanded. Standard OO distance, which you see in your textbook, is 1.3 something in a O2. But here it is 1.51. So it is getting a little bit elongated. And chemists call it activated. And that is what is used for the purpose of a catalyst. And that's what we have done. It can be, this activated surface can be used for CO oxidation. So we now bring a CO, carbon monoxide. This is a carbon monoxide. We bring it. And this activated oxygen, one oxygen, it takes away and goes away as CO2. So CO is converted to CO2, leaving behind one oxygen. Next CO comes, takes away that oxygen and goes to CO2. So both the oxygens contribute to the COs and go away as CO2. And what remains is a pristine HBN overlayer on nickel 111. That's the definition of a catalyst. A catalyst does not take part in a reaction, but it facilitates the, in this case, the conversion of poisonous CO to non-poisonous CO2. So this is something which is a very interesting application of a two-dimensional material, which is hexagonal boron. Okay, so I think I'm through. This is last week's one paper we just got published, and that is on thermoelectricity in transition metal dichalcogenides. Thermoelectricity probably you are aware of, namely it is that there are three quantities which are involved. One is electrical conductivity, one is Seebeck coefficient, probably you remember Seebeck effect and Peltier effect, you remember, okay, in your college days or whatever, I don't remember now. So electrical conductivity sigma, which is a measure of the ability of the electrons to move through the material. Seebeck coefficient, which is a measure of the amount of energy an electron carries across the material. And thermal conductivity, which is a measure of how easily heat can move through the material. So there is a factor called ZT, which is a function of sigma, S, and kappa. And this is, of course, temperature. Okay. So we have tried to see how molybdenum disulfide, when applying strain, can be thought of for an improved ZT. If ZT can be made more than 1, something like 2 or something like that, then that can be utilized as a very good thermoelectric material. So this paper is 2023, last week it got published. Okay, so I think I have shown you about the whole lot of properties of the 2D material. Zoo, structural property, electronic property, magnetic, I did not tell you, but thermodynamic, photovoltaic, photocatalytic, thermoelectric, and optical, both linear and nonlinear, and so on and so forth, all these materials. So the 2D electronic materials family is indeed something which is growing like a tree, and Today, interestingly, you can get an interactive periodic table where you can just click. This is truly interacting. If you are interested, you go into this particular website, and there you can just put your cursor, click on something, and it will show you whether that particular material will form a 2D material or not. Imagine where we have gone. So it is an interactive world of 2D materials, where it will show you whether it is forming a zenes or a mexenes or other kinds of transition metal dichalcogenides, and so on and so forth. So that is where the 2D materials thing have come. And I mean, we still do not know where it is leading us. I mean, what are the other newer kind of materials that we can produce, whose 3D version was known for ages, but the 2D avatar is something which we are now discovering. So that is where. So the epilogue is that today, if you know some interesting 3D material, see if you can grow it in 2D. That is atomically thin layer, and be sure you are in business. So TMDC is one such example. Transition metal dichalcogenide. Believe me, when I started my career in physics, we read this paper on charge density wave and spin density wave. In my 20s, I read those. But today, this layered transition metal dichalcogenides, which we are studying, like MOS2 or MOSE2, okay, these are some of the hottest areas that are being pursued. Okay, so a stage is coming soon, thanks to the sophisticated synthesis techniques, when you order a 2D material with a desired set of properties and you get it. So the most exciting material in the 2D diaspora may yet to appear in the horizon. Those of you who have read Shakespeare's To Be or Not to Be, I don't know whether you have read that Shakespearean literature, the adventure. Okay, so I think we are now in a position we have to slightly modify it and say to be or not to be. That's where I end. Thank you very much for your attention. Thanks.
Thank you, Professor Das, for a most exciting talk. And I learned a lot from your talk today. And I'm sure students have also. So the session is now open for questions from the students and the audience. So anybody can unmute and ask Professor Das directly, or if you have a problem with microphone. Muktish has a question. Muktish, please go ahead.
Yeah, hello, Muktish.
Thank you, Professor Das,
Yeah.
for an excellent lecture. You have already mentioned many behaviors, mainly the electrical behaviors and the 2D materials.
Yeah.
So in the Weinberg theorem,
Yeah.
I think apart from the superconducting and superfluid phase transition, even the magnetic phase transition,
Yeah.
so the 2D, you will not get long range order, magnetic order in the 2D materials. So
Right.
that is just a comment.
You are right. You are right. You do
Yes.
not get the 2D magnetic order. No, the Hohenberg's thing was mostly he proved it for the superfluid and the superconducting phase. But the Marmin Wagner, yes,
Mentioned that, yes.
yeah.
That is the Marmin-Wagner theorem. That is the most general theorem. So actually, my question is for any kind of phase transition, for superconducting, superfluid, even the ferromagnetic phase transition, you need at least 3 dimensions, not 2.
Yes.
Okay, so the fluctuation plays the important role here to destroy the order. So what is the role of the third dimension to bringing the order in the system? So that is a general question. So I do not know what is the answer.
You are absolutely right. See, I mean, if you strictly go, there is some noise which is coming. I don't know whether it is from my end or your end. Something. Wait a bit. Maybe it is from my end. Okay, no problems. Yeah, sorry, Muktish. Yeah, so you are absolutely right. The long wavelength things, that is something for which a third dimension is indeed required. But here, what happens is that for most of these 2D materials, it is very strictly speaking, it is not 2D. There is what is known as a kind of an undulation. You remember I showed you a picture that there are always defects which are present there, and that prevents a material from being a purely 2D. It has got a kind of a ripple. It's called rippled structure. Ripple, R-I-P-P-L-E, rippled structure. And it is that rippled structure which is coming because of the flexural mode of the phonons. That's what I tried to emphasize. That it is that flexural mode which actually is responsible for contributing to the stability of the structure. So strictly speaking, even though we call it a 2D, it is actually, it should be called a quasi 2D structure.
Quasi. And this flexural mode can also be observed even in the case of Magnon. I hope so.
Yes. Oh, yeah. See, we have done a very detailed study. In fact, that last work on MOS2 that I showed you here, that has got this one. If you are interested, this is this is fresh from the oven. So let me just show you once again. You can, yeah, I'll show you this particular one. Yeah, this one. Yeah. See, the in this strain-driven anomalous anisotropic enhancement in the thermoelectric performance of monolayer, here, apart from the fact that our intention here is to calculate the thermoelectric ZT factor, but in the process, this is a paper which is where we have calculated actually all the terms, the electrical conductivity, the thermal conductivity contributed by the electrons and contributed by the phonons, and also the Seebeck coefficient. All of them we have calculated from first principles. And then we have also done something which is called, CRTA, that is constant relaxation time approximation. If you when we teach our students from Ashcroft and Mermin, there is a particular chapter which says about the relaxation time approximation.
Yes.
So in Ashcroft and Mermin, we have that. Now, in these 2D materials, we always try to assume that the relaxation time is sort of roughly a constant value of 1 point something, roughly.
We do not consider the distribution of the
exactly. We do not consider the distribution. But in this paper, okay, if you are interested, you can just have a look at it. It is probably already in print. Okay, in this paper we have actually shown that how the actual estimation of the relaxation time, okay, instead of considering it as a sort of constant, it mimics something else. Sorry for the slight digression. Long time back I was working on the phonon driven superconductivity, where this electron phonon coupling constant in the strong coupling limit, okay, there the expression of lambda, if you see, it contains also which is called mu star. You remember that? Okay. So the mu star is nothing but the electron part. The expression for lambda in the phonon driven type 2 strong coupling limit of the superconductors, okay, there the expression for the lambda contains a mu star. But in 90% or even 95% of the papers, the mu star value is taken to be a constant, some 1 point some value. That's it. They assume that, okay, mu star is roughly constant. But that is not strictly speaking true. There are places where the value of the mu star is not a constant. I mean, you have to calculate it explicitly. And that was something which was done subsequently, that the value of the mu star calculated from first principles and then plugging it in the lambda, that will change the results. Similarly, here, if you take the phonons calculation and do the CRTA, that is the constant relaxation time approximation, which is done by most of the people, most of the workers, okay, if you do that, that will not give you the correct result. So what we have done, we have decided to do the exact calculation of the relaxation time approximation. So these are some of the details which I unfortunately could not go into in my today's talk because of the lack of time. But I mean, those of you who are interested, we can definitely discuss in further details.
Thank you so much.
Okay, Professor Das, we have three questions from
Oh,
three
sure.
of our students.
Sure.
So,
Please.
Somodip Kundu, he says that in the initial slides, you said we can have 2D materials from SP hybridization also.
Yeah.
So, what may be the examples of such materials? SP
Oh,
hybridized.
no, I didn't say. I said SP2. I said
SP2, yeah.
SP2. I said that you see there are the okay. This is for the students. Okay, since this question is asked, yeah, this is something
Yeah,
which
yeah,
is a
yeah.
very obvious question. So in graphite, okay, in ordinary graphite, what happens is that it is the bonding is called SP2 because here every carbon atom has got three nearest neighbors. So the unlike in case of a diamond, which where every carbon atom in diamond has got four nearest neighbor. That is why that is called a tetrahedral bonding, which you have read in your textbooks. So in case of diamond, because of the fact that every carbon atom is coordinated tetrahedrally, that is, there are four carbon atoms at an angle of 109 degrees or something like that. Okay, so the bonding there is sp3. However, instead of four, suppose there are three atoms to which the carbon atoms is linked, and those three atoms can be in the same plane, and that is what constitutes the sigma bond in the it is called sp2 in graphite. Now, what about the third direction? In the third direction, you have got a dangling bond, which is the PZ, you can say. The PZ is perpendicular to the plane of the graphite. And it is the PZ which is which is dangling in case of the pi bond. It is dangling in case of graphene. However, in case of graphite, because of the fact that there is another layer below at certain distance, so there is a very weak coupling between the two sheets. But as far as the in intraplane bonding is concerned, it is purely sp2, purely sp2. But what I said in my initial slide is that it can be spx. That means it can be anything between sp2 and sp3. Yes, that is also possible. Spx means, suppose it is 2.5. What do you mean by that? What do you mean by sp 2.5? Now, that essentially means that there is some kind of a curvature, okay, in the structure which leads to neither pure sp2, which is planar, nor pure sp3, which is tetrahedral. So neither planar nor tetrahedral. So neither sp2 nor sp3. It is something intermediate. This is possible only in carbon. I mean, there may be very few examples in other materials, but in carbon, there is a plenty of such kind of materials that has been discovered via first principles calculations, and also some of them have been synthesized in the laboratory using roots which are sometimes non-equilibrium roots. As a result of that, if you find out the total energy may be higher than that of diamond or graphite. For your information, the total ground state energy of diamond and graphite are almost same. That is nature. We cannot help it. That is why in the nature we have got both diamond and graphite, both. But these intermediate structures of SPX, where it is neither sp2 nor sp3, these can be formed via non-equilibrium routes like laser ablation and these that. There are various ways in which it can be found. It can be formed. And for those of you who are interested, I can tell you that in Cambridge there is a group which is solely in Cambridge University. It is solely interested in the different forms of SPX bonds in carbon, okay, both in 2D and 3D. So I don't know whether that answers at least partly to whatever you have asked.
I think so, yeah.
Okay.
Okay, then next question is from Samrat Rai, and
Yes.
his friend Shagnik also shares the same question. I think they want to clarify a bit about the pseudo spin. You talked about the pseudo spin. So,
Oh, acha. Okay, okay. So let me just. Okay, I think I really I glossed over this because of lack of time. Okay, so let me just. So you see, yeah, I think what they meant is this. Okay, see, okay, the pseudo spin. There is a okay. Now the see the in quantum electrodynamics, okay, the electrons and holes states. Okay, I mean if you consider graphene in this particular case, they are interconnected, obviously, exhibiting properties analogous to the charge conjugation symmetry in quantum electrodynamics. So for the case of graphene, it is the latter symmetry which is a consequence of the crystal symmetry. Now, what is the crystal symmetry here? Because the graphene, it's a low energy quasi particle that has to be described by a two component wave function. Why two component? Because there is, as I showed you, there is a black, blue and a red, two non-equivalent atoms. Okay, and these are needed to define the relative contributions of the two sublattices, that is A and B. Okay, in this quasi particle. So the two component description for graphene is very similar to the spinor wave function in quantum electrodynamics. But that spin index for graphene indicates that sublattice. So in this case, it is A and B instead of up spin and down spin. So we word the spin only in an allegorically. So that is why it is called the pseudo spin for graphene, that indicates the sublattice rather than the real spin. So in the case of sublattice, which is A and B instead of up spin and down spin, so that is why it is called a pseudo spin. Okay, it is usually referred to. Now, before I come to the movement, so this allows one to introduce a chirality, which is formally a projection of the pseudo spin on the direction of the motion, which is positive and negative for electrons and holes. See, it depends on so this particular arrow, this is not a spin, but this is combining the two sublattices. And look, these dotted lines are the lines which are joining the two sublattices, and this particular arrow is something which is orthogonal to that. So when these planes move, these planes are described by this particular vector which is defining perpendicular to that. And so whether here I have given, for example, the 30 degree. The 30 degree means when you are joining the particular lines of the two sublattices in one particular direction. So there are these are the directions that precess, just like a spin precesses, and this is what is called pseudo spin. And the pseudo spin is something which very nicely describes the graphenes, the two sublattice model. That is why I mentioned it as a pseudo spin.
okay.
If you are interested in more, I can give you some details.
Yeah, I think they have understood most of it, I think. So Mitra Kundu, he is curious about the Marvin-Wagner-Weinbach theorem, where it is stated that the continuous symmetry cannot be broken for dimensions d less than 2. So you mentioned that this makes fluctuations important. His question is fluctuations in which quantity exactly?
Okay. Now, see the fluctuation. Yes, the fluctuations are important. The fluctuation is which one? Now, in this case of graphene, I mean, some of the plausible fluctuations are the phonons which are leading to the movements orthogonal to the plane. The movement orthogonal to the plane, that is where is the direction in which the fluctuation takes place. Okay, I mean it's something which is in not in the same spirit as it was defined in case of Marvin Wagner for magnetic cases. or by Hohenberg in case of superconducting cases, because the graphene is existing, and I mean it is stable. That is all well known. So does that mean that this the so-called instability that they are talking about in a pure 2D material is something which is preventing graphene to form? The answer is no. So which is correct? Is it that the existence of the fluctuation is something which is correct, or there is something else which is happening? Now, my feeling is that the existence of the fluctuation is something which has to be correct. That cannot be ruled out. But it is the long wavelength phonons that get affected. In this particular case, I think the flexural mode is something where lies the main dichotomy as to whether the fluctuation can be dealt with via the flexural mode. That is all I can tell at this point. Yes.
Okay. And then one more question. Shouvik Chatterjee, he asks this: what exactly is responsible for the shift of the nature of the band gap of transition metal dichalcogenides once it is thinned down to monolayers? What exactly is responsible for the shifting of the band gap?
Yeah, that's a very good question actually. Okay, now you see, yeah, again, I did not go into that details, but that's a very relevant question. Thanks for the question. See, there are two things. I will just add a few more. Add one more point. It is not only the shifting of the band gap, but also it is the shifting of the nature of the band. That is, it quite often goes from an indirect band gap to a direct band gap semiconductor. And also the value of the band gap changes from 1.2 to 1.9. I mean, that's what we have seen. So what happens is that it is the, as a function of the number of layers, one can actually see that when the number of layers is, let's say, bulk, and then gradually you thin down 10 layers, 5 layers, 3 layers, 2 layers, and 1 layer. Now, we have actually seen by our calculation for multiple layers that the band gap is still indirect and with a certain value. But the moment you come to a monolayer, the situation changes drastically, not only in terms of the value of the band gap, but also the nature of the band gap. And this change is presumably because of the hybridization that takes place between the transition metal and the chalcogen atoms. You see, in a monolayer transition metal dichalcogenide, okay, you have got the two chalcogen atoms on the two sides of the transition metal. Okay. Now, suppose instead of one monolayer, there are two monolayers, or three monolayers, or four. Then there are screening effects which take place between, say, layer number 1 and layer number 2. Okay, because of the fact that you have got two chalcogen layers, one above the other. But in case of a single monolayer, that does not arise. So it is the screening effect that is present when you go to multiple layer, and it is absent when you go to single layer. So a single layer, or you can call it a monolayer or a tri-layer, whatever you call it. Actually, strictly speaking, MOS2, you should call it tri-layer, because it is 3 layers. One transition metal with sandwiched between two sulfur or selenium or whatever it is. Okay, so a monolayer or a tri-layer, whichever is the definition you call it, okay, has got this uniqueness in the sense that it does not have the option of the two successive chalcogen layers screening the effect that ultimately in turn affects the hybridization between the molybdenum D and the sulfur P. It is the PD hybridization that is the most predominant in when it is trying to manifest the different properties of anodes. That's it.
Okay. Muktish, I still see your hand raised. Do you have a question? Because Purna must be quite tired. Uh, you still have a question? No, I don't think. I think it got stuck there or something. Am I audible? Purna, can you hear me?
Yeah.
Hello?
Yes, you are audible.
Muktish, you have a question still?
No, no, no.
Oh, okay. Okay, in that
That
case,
is,
I don't think there are any more questions, and we all should thank heartily Professor G.P. Das for a wonderful exposure to the world of two dimensions. Thank you, Professor Das, for being with us today. So, with this, I conclude this colloquium session. But I would request Professor Das to stay back for 2-3 minutes because I have something
Sure.
to discuss with you
Sure.
regarding something.